Okay, guys, welcome to Let's Get to the Marks. Today, looking at a little water of crystallization question, practical based question. We're just going over some techniques you need for A-level chemistry. All right, let's get into it. It's a little bit on complex ions and colors as well. So let's go. Question two. Ammonium cobalt 2 sulfate is made by mixing aqueous solutions of ammonium sulfate and excess cobalt 2 sulfate. A. Dry crystals of ammonium cobalt 2 sulfate, NH4 2, SO4.CO, SO4.6H2O are obtained by this following procedure. So we've got step one here. The reaction mixture is transferred to an evaporating basin, heated gently, and then left to crystallize. So the step two, the crystals are separated by gravity filtration. And then step three, the crystals are then rinsed with a small amount of ice cold water. And step four, the rinsed crystals are placed in a warm oven for 30 minutes. You should pay attention in questions like this when the exam board have put certain words in dark black, in bold. They want you to pay attention to those words, and you'll probably be asked that. Part two, the color of the cobalt sulfate solution used is pink due to the complex cobalt 2 ion, CO H2O6 2 plus. Explain why the solution is coloured. Yeah, at this point I say grab a bit of scrap paper, press pause on the video and have a go, and then unpause to do a walkthrough of the answer. So with this cobalt 2 sulfate solution, and we've got this complex cobalt 2 ion, COH2O6 2 plus. Remember, what are those water molecules, the H2Os? They're known as ligands. They can donate their lone pair of electrons on the oxygen atom to the cobalt 2 plus ions. Now what happens is the ligands have this little lone pair of electrons, and there is an electrostatic repulsion between the lone pair of electrons on the ligands and the electrons in the 3D orbitals in cobalt. And what happens is the 3D orbitals in cobalt are pushed apart because of this electrostatic repulsion between the ligands and the 3D orbitals. What do you have to know for A level? You just need to know that ligands cause the 3D orbitals to split. Now you can refer to the 3D orbitals as a subshell because it's a 3D subshell. But you can just say the 3D orbital split. What does this mean? Well, we've got 5 boxes there. Say like 2 go to a higher energy level and 3 go lower. So we end up with the 3D subshell. Not all the electrons, all those orbitals, the spaces where you find the electrons, are at the same energy level. Some are at a lower energy level, some are at a higher. So that's fine. We've got that. Now, of course, you've got light from the sun, from a torch, from whatever. You've got light all around us. Now, light that actually hits these 3D orbitals can excite electrons. When the electrons in the lower subshell absorb some of the energy from the light, or the photons, you can say visible light or photons, the electrons become excited, or we can say promoted, to the higher energy level in the 3D subshell. So some of the little arrows I've drawn there can leave the boxes at the bottom and join the boxes at the top. Now we're talking about visible light. What is visible light? We're talking red light, orange light, yellow light, green light, blue light, indigo, and violet. We're not talking about infrared or ultraviolet light beyond the visible spectrum here. We're talking about photons of light. You can mention that if you like. They're absorbed by the electrons and they move up to a higher level. Now, different ligands, we're using water as the ligand here. Different ligands will can either create a bigger gap between the split or a smaller gap, and the size of that gap will is linked to the wavelength of light that's absorbed by the complex ions. Now, what we say is that the light that's absorbed by the complex ions, well, that's gone. You can't see that light. So if it's absorbing red light, the mixture won't appear red because red or orange has been absorbed. So it's not going to appear red or orange because the orange light has gone into the electrons. The light that's left over, that's reflected or transmitted, which means goes through the beaker of solution or bounces off of it, that's the light that we see. And we call that the complementary wavelengths. So the wavelengths that are absorbed, they're the absorbed wavelengths of light. And then the other colors, we call them the complementary wavelengths of light. They're the ones that we see. And why do we see them? Because that complementary wavelengths are reflected or transmitted through the solution, and that's why it appears pink. So your 4 marks here are really for saying ligand splitting, and then for saying light is absorbed by electrons. That's the second mark. Then the third mark is to say those electrons are promoted or excited, or they jump to a higher 3D energy, to a 3D orbital, not level, because the whole thing is on the same level. So they go to a higher orbital, and then depending on the wavelength of light absorbed, we see the complementary wavelengths of light are transmitted or reflected, and this is what gives the cobalt ions the pink color. So really, you've got marks for splitting, marks for absorbing light, marks for exciting and promotion, and then marks for the complementary wavelengths that are transmitted or reflected. And that's really where you get all the marks for this question. All right, we're going to move on. Okay, guys, don't forget I took this question from an Edexcel A-level chemistry paper, but if you're doing OCR or career, you still need to know this content. So don't turn your nose up at it. It's well worth you being able to do it. All right, let's move on to the next part of this question. Now, explain the shape of the cobalt 2 ion COH2O 62 plus using electron pair repulsion theory. So what we're looking at here is what shape does it have? Well, it has, oh my gosh, I'm writing in white. That's a bit daft. Okay, so to explain the shape, the shape that this ion has is octahedral. It's got 6 ligands. And those ligands, what is a ligand? They can obviously contain a pair of electrons available to donate to the positive transition metal ion. Now, they form 6 bonds around the transition metal ion. So we've got 6 bonding pairs around the transition metal ion. That's going to get you a mark, which is why we have an octahedral shape. What do those 6 pairs want to do? Well, they're all pairs of electrons, so they want to get away from each other. So in order to minimize the repulsion, this is the arrangement they form. This is like the furthest apart they can get in terms of the 3 dimensions that are available. And so you don't have to draw a diagram, but you can pick up marks if you've drawn the diagram and you couldn't put this into words. So for the octahedral shape, we just want to put our 6 ligands, 1 ligand above, 1 ligand below in the same plane, direct above and below, and then a kind of square planar shape in the middle. So you've got the dashed lines going into the paper with a water molecule coming out, and you've got these solid black lines coming out of the paper towards us, and that's part of the square planar bit of the octahedral. And really, I shouldn't draw any of the bonds like this one here. I've drawn this solid black line going to the hydrogen on the water. Hydrogen doesn't have a lone pair. So technically, I should redraw that and put the oxygen next to that bond. So it's OH2. It's still H2O, but I've written it in that order just to show that the bond has to attach to an oxygen because the oxygen has a lone pair and the hydrogen doesn't. It's kind of a little technicality. So I can really write this as H2O here on the left as well with the oxygen above that dashed line. Okay. And of course, octahedral, what does that look like? Hard to visualize that shape, but it's actually a diamond shape. So if you think of the traditional diamond, where you have 2 pyramids with the bases touching. Now, I got D in GCSE art, as I always go on about. So yeah, I'm not going to attempt that too much. Let's move on. So the next question says, give the reasons for carrying out steps 3 and 4 of the procedure, referring particularly to the words in bold. So whenever they've got these words in bold, they really want them. So they've got the reaction mixture, evaporated it, blah, blah, blah. The crystals are separated by gravity filtration. So we've let the remaining solution drip off using gravity. The crystals are then rinsed. So why rinse the crystals and then why in ice cold water and then why stick them in a warm oven is essentially the 3 things we want to know. Why rinse them? Why ice cold? Why warm oven? So we rinse the crystals. Just because we've used gravity filtration, there may be some remaining solution stuck to the crystals, which may have soluble impurities in it that we want to get rid of. So we rinse the crystals to remove any remaining solution that may contain soluble impurities. It may even or excess solution. So it may have some of the excess solution that we just want to get rid of. and that's why we rinse them. So that's the first word in bold. The next word in bold was ice cold. So ice cold water is used. So the solubility of the water remains low. If we start using hot water, we increase its ability as a solvent to dissolve crystals. We don't want to re-dissolve. So we want to avoid re-dissolving, or yeah, we don't need to go into all that. To avoid dissolving the crystals. We don't want to actually dissolve the crystals we've just made. If we used hot water, we're going to increase the chance. Obviously, you're going to increase the solubility of the crystals, more soluble in hot water than in cold water. God, it's a bit difficult for me to speak, isn't it? Right, let's do the last bit here. So what was the last bit? Why did we dry them in an oven? Obviously, we want to dry the crystals. Simple, isn't it? So dry, oh, it was warm oven, wasn't it? Dry in a warm oven um, to dry the crystals. Um, but uh, do basically they're focusing on the word warm, but do not use hot oven as the crystals could melt. So we don't want the crystals to melt, or as the crystals contain that dot H2O, water of crystallization, or the water of, whoa, crystallization could evaporate. Now that wouldn't be good because that's part of the product that we tried to make is that dot H2O. You know, when you get the water of crystallization, it's going to say like dot H2O, those water molecules that are within the crystals, trapped within the crystals, they might start evaporating and that's going to change the crystals. So we want to avoid that. Okay, let's go to the last part of this questione. The percentage yield of this reaction is 70%, not great. Give two possible reasons other than an incomplete reaction why the yield is less than 100%. So really, it's to do with the steps. So whenever you're asked about yield and how to improve it, or what's the reason why we haven't achieved 100%, which you'll never achieve, you'll find it in the method. So it's transferred to evaporating base and heated. So when they're heating, some of the crystals may have spat out of the evaporating basin. Okay, some of the stuff may have spat out. So you might have lost a little bit of mass like that. The crystals were separated by gravity filtration. The crystals are rinsed. Okay, so in the filtration process, some of the crystals may be stuck on the filter. So when you rinse the crystals with ice cold water, some are left behind in the filtration paper. Crystals are then rinsed with a small amount of ice cold water, rinse crystals placed, and then in a warm oven, some of this, the water of crystallization, the dot 6H2O, may actually evaporate. And that means that your mass will be less than expected. And therefore, when you calculate your percentage yield, it's going to be lower than expected. So those are our reasons. Let's go down and type them up. Don't forget, you can email me at letsgettothemarks@gmail.com and leave any comments or suggestions for particular exam questions you'd like me to go through. You can leave them in the comments also down below on this video, and I will get those done. So, all right, smash the like button, punch up the bell. Let's get to the marks.